Okay, welcome back to our next lesson. This lesson begins on page 22, and I'd like to sort of start off where we ended off with the last lesson. One of the fundamental problems in mathematics centuries ago was how do we get the slope of a tangent line to a curve? Let me just suppose here's a nice curve. This, like I say, is on page 22. Let me just draw a tangent line that, now again, I'm not going to be able to do it very well because I can't use a ruler here, but I'm going to try to draw a tangent line at this point right there. Now, again, you'll notice that this graph, there is no numbers on the x-axis, there's no numbers on the y, so we really don't know what the coordinates are. So I'm just going to call this first x value right there, let's be imaginative. Let's just call it x, eh? All right. So let me try to draw what the tangent line would look like. I'm going to try to do it as well as I can. I can't use a ruler, remember. Okay, so there. Let's suppose that's your tangent line, and it's intersecting the curve at that one point. Now, of course, the problem is, unless you're going to estimate a second point somewhere on that line, we really can't exactly get the slope of that tangent line because, again, there's only one point. How in the world do you use the slope formula if you only have one point? All right, that's the fundamental problem. So let's suppose that this is our tangent line again. I'll put a little t there for tangent line. And now, of course, if this is my x value, we know that right across from that, over here somewhere, this is the y value corresponding to that x value, isn't it? And to get the y value, of course, another way we can say y is we can just say that's f of x. So here's your x down here, and here's your y over there. So at least we have the coordinates of one point. Well, what we can do, what mathematicians did years ago, was they said to themselves, well, you know what? If we can't get the slope of that tangent line, why don't we draw another line that's kind of very, very close to that tangent line, but intersects that curve in 2 points? And remember what we call that kind of a line? That's actually called a secant line, isn't it? So here's what they did. They picked this first point. We can still use the first point, the point of tangency, where the tangent line touches the curve, but let's pick another point, say about, well, I don't know, let's say about here somewhere. See that? That's on the curve. And of course, we can draw the secant line through those 2 points, and it would look something like that right there. Okay, now I'll put a little s there for secant. Now you can see that even though the slope of that secant line is not exactly going to be the same as the slope of the tangent line, it's not bad. It's fairly close. It's a rough estimate of what it is. Now, what do we call this? If you were going to calculate the slope of that secant line, now you would need down here, you would need that second x value, wouldn't you? And the triangle that we're going to draw to get the slope of that secant line looks something like this. Okay, so there's your right triangle. Remember now, rise and run. That's what we're going to want. Okay, so let's suppose that this triangle that we've just drawn to get we need the slope of that now, the rise and the run. Let's suppose that the base of it, we'll call that h. Right, we'll call that h. So the width of our triangle is h. And of course, if this point here is x, and you add h to that, then this x value must be x plus h. Well, that's our run. That's the run of the triangle, isn't it? H is the run. Now, what is, if this is my second point, I'm also going to need, way over here, I'm going to need to get that y value, right? Well, we get that y value by plugging x plus h into the function. So this y value would actually be f of x plus h. So there's your y value. So we've got our two y values. We've got our two x values. Now we know that the run is h, but here, look, what's that rise, I wonder? What's that rise going to be? Well, ordinarily you'd say y2 minus y1, wouldn't you? That's what the rise is, y2 minus y1. Well, by golly, here's your y2 right there, and here's your y1. So it turns out that this rise right here is actually f of, instead of saying y2 minus y1, you can say f of x plus h, that's your y2, take away f of x, that's your y1. See that? So there's your rise, h is your run. So in other words, the slope of this secant line is equal to, now watch the formula, y2 minus y1 is just f of x plus h minus f of x, that's your rise, and the run, well, the run is just h. You see that? There's the slope of that secant line. Now you could pick various points for x, and you could decide how wide you want to make that triangle, or how close you want to make those 2 points. And that's the slope of the secant line. And you know what? It's not bad. It's a pretty good approximation to the slope of the tangent line, but it's not exact. Now, the question is, how could we make it more exact? How could we take that secant line and make its slope even closer to the slope of the tangent line? Well, the answer to that would be, if you look down just under the diagram, you see this? What if we made those 2 points closer together for the secant line? In other words, what instead of having the point way up there, what if we had the point right here and got that slope? Well, by golly, you know what? That'd be even better. What if we picked the other point right here on the curve? Well, again, that would be even better still. And in fact, if we could make that distance, or in other words, this h, right? You're trying to make it as small as you can possibly make it. What if you could make it so small that it's almost touching the first point? Well, then, by golly, your slopes would be almost indistinguishable. Now, I've got a little demo here that another instructor here, Mr. Scott Skanes, he emailed this to me, and I'm going to show this to you. And it's a little activity that he did up on Desmos. Let me explain what's going on here. Do you see this nice blue curve? Oh, it's a pretty exotic looking curve. We're not sure what it is. Could be a trig function of some sort. But the green line is a tangent line at this point right there. Do you all see that point? There's your point of tangency. And the green line, the green tangent line, touches that curve at only that point right there. Now, according to Desmos, they've actually calculated the slope of that tangent line. And if you look over here in the right-hand margin, right at the very bottom, see what this says? M, slope of the tangent line, is equal to 1.177. Now, Desmos is actually able to calculate it exactly. That really is the slope of that tangent line. Now, Mr. Skanes also put in another line. You see this is kind of like a purplish color. I don't know if you can see the color in that. The color doesn't matter anyway. But here's another line that also goes through the point of tangency, but it's got a second point intersecting the curve right here. Now, this is a secant line. And in fact, remember now 1.177. I wish I could draw it here, write it down, but I can't use my marker when I've got Desmos open. I found that out the hard way. Here is the slope of the secant line. Now, right now, again, Desmos has calculated it to be approximately 0.237. The slope of the tangent line is, again, about 1.177. Now, I'm able to, this is pretty good what he has done here, Mr. Skanes has done. I'm going to sort of take my cursor, and I can drag that point, and you see what's happening. As I move this point along the curve, over here, Desmos is recalculating the slope of that secant line. Now watch what happens as I bring these 2 points closer together. The closer I make them, you see that? The closer the secant line is starting to look like the tangent line. And in fact, the slope is getting closer and closer and closer and closer to the slope of that tangent line. And in fact, if you look right here now, the slope of the secant, now we're up to 1.005. The slope of the tangent, remember, was 1.177. Now watch as I bring it even closer still. Keep your eye on that secant line slope. See, it's getting bigger and bigger and bigger and bigger and bigger and bigger. By golly, look at that. It's almost 1.177 now. But watch what happens if I put my 2 points directly on top of each other. Bam, undefined. Why is it saying that? Why is it saying that the slope of the secant line now is undefined? It's supposed to be exactly the slope of the tangent line. Well, the problem is a secant line, if you want to get the slope, it needs 2 points, not 1. So even Desmos is struggling with this. Now, if I bring my other point down below, you can see now the slope is still getting bigger and bigger and bigger, and now it's up to 1.235. But by golly, you know what? It's too bad. It's too bad I can't have that point line right on top of the point of tangency. All right, but the thing is you can't. You see that? That's the problem. You can't make, let me go back to the notes, you can't make h equal to 0. Now let me put this here. You can't make h equals 0. You can't make that triangle so small or those points so close together that the 2 points actually merge into 1. Because look at what's happening with your slope. See that? H is in your denominator. If you put in a 0 for h, ladies and gentlemen, not only does the denominator become 0, but the numerator becomes 0 as well. So let me say that again. Let me stress that again. You can't just put in 0 for h. You can't do it because you get an undefined expression. But you can get them closer and closer and closer and closer and closer until they're practically touching. Now, I got a question for you. Where have you heard, in just the last few lessons, where have you heard a technique something like that, where you can make something get closer and closer and closer and closer to a value, but you can't actually make it that value? That's limits, isn't it? And that is why we spent the first part of this unit going over limits. So even though you can't make h equal 0, by golly, you can take the limit as h goes to 0. So what we're really going to do, here's your slope, remember, that's your slope. It's the slope of the secant line. But if you want to get the slope of the tangent line, here is what you calculate. Now look at that, very important. That actually is m, whoops, oh, I didn't mean to do that. Let me put down m of the tangent line. You see that? If you could take the limit as h goes to 0, in other words, if you could make that triangle up here, if you could make its width 0 or as close to 0 as possible, then what you end up with is that the slope of the secant line is exactly the slope of the tangent line. And that, ladies and gentlemen, is where this formula comes from. This is probably one of the most important formulas that you in your young lives have ever seen in mathematics, especially with regards to calculus. All right. This is such an important formula that it's actually been given its own name. Let me just write down here, first of all, that it's the slope of the tangent line at some point x. All right, and again, x you can get from your graph. The name of it is, whoops, no, not an R, sorry, whoops. The name of it is called the derivative. All right, you might have heard of that word before. In fact, one of the branches of calculus is called differential calculus, and that's where we get the derivative. All right, because from that word. And this technique, by the way, this method for calculating the slope of a tangent line is also referred to as the delta process. All right, it's called the delta process. Now, the reason it's called the delta process, well, you've done science before, right? You know that delta is a symbol that stands for change in. Delta T would be change in temperature, things like that. Well, in some textbooks, in some approaches to this technique, instead of using H for the denominator, or for the width of your triangle, some textbooks actually use delta x, the change in x, and then that's a good method to use as well. So you would see, if you were to see other textbooks involving calculus, instead of saying the limit as h goes to 0, some textbooks actually show the limit as delta x goes to 0. All right, so it's no big different. It's no big deal. We can still use h. That's fine, but that's where the delta process comes in. All right, because like I say, some textbooks use delta x instead of h. And this, ladies and gentlemen, this delta process, this will actually calculate the slope, not approximate. It will give you the exact slope of a tangent line at any point, any value of x that you want it to. And it's pretty powerful stuff. It's really powerful stuff, in fact. Let's have a look at the example here on page 23. Now, what are they asking us to do here? Okay, here's a nice looking curve. What does the example want us to do? Estimate the slope of this curve. Okay, so f of x equals x squared. That's the function, remember? F of x equals x squared at the point 1, 1 by using secants at the points where x equals 2 and also where x equals 1.5. Well, I tell you what, I'm going to change that a little bit. I'm not going to use those points right there. We'll use 1, 1. We'll use 1, 1. Actually, I'll write it down here because that is the point of tangency. And we'll also use the point, now let me see, let's pick out another point here. So there's 1, 1. We'll use that. Well, let's try this one, 2, 4, right up there. All right, because I can see what those coordinates are. So what I'm going to do, everybody, is I'm going to approximate the slope of the tangent line at this point, right there, by actually getting the slope of the secant line. Now, you can see it's not going to be the same thing. And in fact, those 2 points are kind of far apart. But let's estimate the slope of that curve at the point 1, 1 by using that secant line. So let me go. Okay, so here's the slope of the secant, S-E-C-A-N-T. And we can still just use y2 minus y1 because now we have the 2 points, you see. I'm not going to use the delta process here because I actually have 2 points. So let's call this one x1, y1. And let's call this point x2, y2 right there. So we'll get the slope of that secant line. I can see it's positive something. It's fairly steep. In fact, if you count your squares, you could probably tell what it is anyway. You could even do it that way. So we're going to have 4 minus y1 is 1 over x2 is 2, x1 is 1, 4 take away 1 is 3, 2 take away 1 is 1. Now look at that. There's the slope of that secant line. The slope of the secant line is 3. Okay? Now, we're actually going to, for the first time, we're going to use the delta process on f of x equals x squared. That's a pretty simple function right there. Now they say find the slope of the tangent line at the point 1, 1. So what we're going to do, now they might want us to estimate it, but I'm going to go further. I'm going to get the actual slope. I'm going to use the delta, DEL. I'm going to use the delta process here. And by golly, all right, we're going to get the actual slope. So remember what the function is now. Let me just write the function right here. F of x equals x squared. And we want to get it at the point 1, 1. So x is 1 and y is 1. All right. So remember now what your formula is. The slope of the tangent line is equal to, now we're going to use the delta process. So it's the limit as h goes to 0 of f of x plus h. Now you should know what to do there. You plug x plus h into the function. Minus f of x all over h. Now again, note carefully, you cannot just plug a 0 in for h. You can't do it because if you did, you'd get 0 over 0. And no one knows what that is. That's undefined actually. All right, so here we go. Here's our step number 2. So this is the limit as h goes to 0 of, now f of x plus h, of course, means you plug x plus h into the function in place of x. And what that's going to turn into is x plus h squared. All right, so I just plugged x plus h into the function f of x. Minus this part right here just means the original function. So in our case, the original function is x squared. Now, please make sure you put brackets around this f of x because, do you see that minus in front of it? If that was a more complicated expression, if that was a binomial or a trinomial, that minus in front would matter. All right? Because then you'd have your signs changing. So please make sure you put brackets around the f of x part. Okay, let's keep going. Now remember, I still can't just put in 0. I can't just plug in 0, because if I did, I'd get 0 over 0. So it's equal to the limit as h goes to 0 of, now you square out x plus h. Now remember, ladies and gentlemen, I'll stress this again, multiplying a binomial times itself is 4 multiplications, isn't it? 1, 2, 3, 4. So this first part would become, and again I'll use brackets, you're going to get x times x is x squared, and then x times h, and then another x times h, so that's plus 2xh, and then plus, and finally h times h is h squared. All right, so there you go. I squared out that binomial, minus x squared. I can remove the brackets there now in that second part if I wanted to. All right, but make sure that when you remove it, if it was, like I said, if it's a binomial or more, make sure that you change your signs. So let's keep going here now. Just remove the brackets. Just remove the brackets. And something nice happens. And something nice usually happens, practically always happens. The x squareds cancel. So all you're left with is the limit as x, or as h goes to 0, sorry, of 2xh plus h squared over h. Now you still can't put in 0. You still can't use direct substitution because, again, you'd end up with 0 over 0. So remember, we try some kind of algebra, don't we? So this is equal to the limit as h goes to 0 of, now, do you notice that there's a common factor in your numerator of h? So we'll remove the h. In fact, even if there was another common factor, I would not remove that. So this becomes a 2x plus, and now there's just a single h left, divided by h. And now look at what happens, ladies and gentlemen. Those h's cancel out. They cancel out. So now all we're doing is taking the limit as h goes to 0 of 2x plus h. Now you can plug it in. Now you can use your direct substitution, because once you plug it in now, you're going to get 2x plus nothing. And look at that. There is your slope. Now, do you notice it's not just a number, is it? It's another function. And that is actually the derivative of the original function. Think of it as a slope function. Now, you can put any value of x that you want into that derivative, into that slope function, and you will get the slope of the curve at that point. Well, remember, we wanted to get the slope at this point right here. All right, now that point, remember, is 1, 1. Well, if you look at the derivative, if you look at the slope function, there's nowhere really to put the y here, is there? There's nowhere to put the y. So if you want to get the slope at x equals 1, so the slope at x equals 1, well, you just plug 2 into it. Or sorry, 1 into it. And there you go. There's your slope at the point 1, 1. And now if we go back and look at the graph, okay, remember the slope of the secant line was 3, but the slope of the tangent line is really 2. Look, this is the first time you've ever used the delta process to come up with the slope or the derivative of a function. That was a pretty simple function, but for the first time, you've actually calculated it. All right? All right, so I tell you what, I'm going to stop this video here because it's over 25 minutes in, but I'm going to do up another video right after this one. We're going to be looking at this delta process in a little more detail. We're also going to learn some other symbols and terminology that we use for the derivative. Okay, but by golly, this is a very important technique right here. Hundreds of years ago, when mathematicians first figured this out, this was pretty powerful stuff because for the first time, they were able to exactly calculate the slope of a tangent line to a curve. And that opened up all kinds of different types of techniques for solutions to solving problems that before that were unsolvable. They could not come up with exact solutions, and suddenly they could. All right, so I'll stop this video here and I'll start the next one. And bye bye for now. I'll see you in just a few minutes.